Hi class, welcome to the next video, section 13.2. Today we're going to talk about finding limits algebraically. So this is where we use math to find our limits rather than plugging in a bunch of values or trying to graph or look at the graph of our function, right? So here we're going to analyze a function using the algebraic methods that we know of and try to find our limits that way, okay? Now these don't always work. Sometimes we have to use a numerical method or look at a graph. Even looking at a graph at times isn't going to work, and we have to resort to numerical methods. Once we get into calculus, we will learn some methods that will pretty much work for all cases at that point, using algebra and calculus together. But at the moment, for a large section of problems, the algebraic methods will work, okay? So first we have to talk about continuity. A continuous function is a function that you can draw on a graph without ever lifting your pencil off the paper. Now that's not the rigorous definition by any means of what a continuous function is, but that's the layman's definition. The rigorous definition is a much more complex. So the layman's definition is much easier for people to understand. Okay, so a continuous function is a function that you can draw all with one swoop. You never should have to lift your pencil off the paper, technically, to draw a continuous function. That's why it's called continuous. There's no breaks, there's no jumps, there's no gaps, there's no holes specifically. It is just one smooth continuous function. Okay. If a function is continuous at a point C, right, the point of interest to us that we've been using for finding limits, then the limit of our function as x goes to c is just f of c. So this is really nice. This is actually very powerful, because if our function is continuous, to find our limit, all we have to do is plug in c to our function. Very nice. Okay. Now the problems that we're going to run into and the problems that we deal with in calculus are when we're not continuous at the point of interest. Okay. So let's talk about some of our common continuous functions. Okay. Continuous functions consist of polynomials. So if we're ever asked about the limit of a polynomial at a point, we can just plug that point into our polynomial and we're fine. Polynomials are always continuous. Okay. Power functions are also always continuous. Things like 2 to the x, 1/2 to the x, right? Those are power functions and they are always continuous. Are exponential functions, which are related to our power functions, right? So things like e to the x are power functions. Lines are continuous. Cosine is a continuous function, and sine is a continuous function. These are the general continuous functions. You'd be hard pressed to talk about any other functions that are continuous. Natural log tends to be continuous, although it doesn't cover all of the reals, so that's why it's not included here. Tangent is not continuous. Things like that, right? So these are the ones that we generally think of when we're talking about continuous functions. There's going to be times, again, where we want to, the point that we want to evaluate our limit at is not continuous in our function, right? So when that happens, we have to, the easiest way to deal with it is to manipulate our function using algebra, okay? Possibly this is a rational function, and our point of interest is a point that makes the denominator 0. Well, there's ways to move around that, okay? Maybe there's square roots that are showing up. Maybe my cosine function is 0 at this point in the denominator, right? So there's things that we can do, right? Some of the techniques that we use is rationalizing the numerator if we have a radical, okay? So up to this point, we've mainly focused on rationalizing denominators, but there's going to be times where we're going to have to do the opposite and actually make the numerator a rational function, rational term, and introduce a radical in the denominator to get rid of this point that may be causing us problems, okay? Maybe we have to simplify our rational expression. Maybe there's a common factor where our point of interest is a 0 in the numerator and denominator, and we can just cancel it out, okay? So there's things that we can do. We have to be kind of crafty when we do these, right? So let's start with an example. Let's take this rational function, right? And we're looking for the limit as x goes to -1. Now, as it stands, we can't really tell what's going on at -1, so generally we like to factor these things. Okay, so what we're going to do is we're going to factor so we can figure out where we're discontinuous, because if I plug in -1, especially since I just talked about it, this probably makes the denominator 0, right? So we're trying to be aware of holes and vertical asymptotes, because that makes our function not continuous, right? So I take my function, I factor it. You should all know how to factor at this point. If not, go back to chapter 3 and look at synthetic division, your rational zeros theorem. This denominator factors to this form, and the numerator factors to this form. Notice that if I take -1, that will make this term 0. It doesn't do anything for these two, but it does for this one. So I can't just plug in -1 because I'll be undefined, right? My point x equals -1 is a whole because that factor also shows up in the numerator. So this isn't actually an easy case, because what I can do is I can just cancel out those two terms, right? So the limit of this function, which is the same as the limit of this function, is the same as the limit of this function. It's the same function, I've just simplified it, right? So I cancel it out the whole. So now I can plug in -1 into this function because it's continuous at this point, right? So when I plug in -1 everywhere and calculate the value, I get -6/4, or -3/2. So even though there's kind of a lot of math, not really too much. I mean, factoring can take a little bit of time, but it's faster than trying to graph this by hand, right? I know that's not what you would do, but it's faster than graphing this and trying to see what happens. Sometimes it's hard to tell what the whole is, and it's a lot faster than using a numerical method of plugging in several values into this complicated function, right? So our function is not continuous at this point, but the left and right hand limits approach the same value as they approach the same value. So the limit does exist even though the function is not continuous there. So I cannot evaluate the limit by just plugging in -1, but I can by simplifying first and canceling it out as a whole, right? Because the limit does exist even though it's not continuous at that point. The left and right hand limits agree. I just don't have an actual value at that point. Okay, so for this next example, let's take the exact same function, but look at what's happening as x goes to 5. So we already drew the graph, so we can look at the graph. If we're looking at 5, we do have a value here. Okay, and so same exact function. 5 is not a whole. It's not a vertical asymptote for our function. We've already factored the denominator. We know it's all ones and +1 and -1 in the denominator as far as zeros go. So I'm continuous, right? Even if 5 made the numerator 0, that wouldn't make it discontinuous, right? It'd still be continuous. It'd just have an output of 0. Anything as long as the denominator is not 5, right? Or not 0, I should say, is fine. So I can just plug this in and we'll be okay, right? So the limit as x goes to 5 of this function, this rational function, is just me plugging in 5 everywhere, right? So everywhere I see x, I replace it with 5. And we'll just simplify that down. It comes down to 252/96. And again, right, we just keep simplifying until we're done. So my simplified value is 21/8. So that is the limit of x over 5, which should make sense. If you go back to our graph, we'll see that that's the value that approaches, right? This is a little bit more than 2, right? Too far. Okay, so for 5, we have a little bit more than 2, right? Less than 3, more than 2. So let's do another example. Let's say I want to find the limit as x goes to 0 of the root of t squared plus 9 minus 3 over t squared. Okay. So I can rewrite this by rationalizing the numerator, because I have a problem here. If I plug in 0 to the denominator, then I don't have anything. Okay, so I have a choice of looking at a numerical method by approaching 0 from the negative side and from the positive side and seeing what I get, seeing if they agree. Another method is to rationalize the numerator, right? So I have my function. I'm going to take it, I'm going to multiply it top and bottom by the radical conjugate of the numerator. Okay, so here I'll have t squared times this whole thing. It'll distribute to both terms. So notice there's two terms, the square root term and the 3 term. And here I will have a difference of squares. So I'll have t squared plus 9 minus 9 on top. Okay, on the bottom, t squared times the square root and t squared times 3. So 9 minus 9 will go to 0. And notice that I'll be left with a t squared, and a t squared. So those actually get to cancel, right? If I pull out that common term, which is nice because now I don't have any more t squareds in the denominator. And if I evaluate at 0, I'm no longer in a non-continuous situation, discontinuous situation. So this just turns into 1 over 3 plus 3, or 1 over 6. Okay, so my limit of this function as t goes to 0, I can evaluate by rationalizing the numerator in order to get rid of this troublesome denominator that I have, right? So now let's go over some of the properties that we have of limits. We can use these also to evaluate our limits. So let's say that c is a real number, okay, and that the limit as x approaches a of f of x and the limit as x approaches a for g of x both exist. So I'm approaching the same value for two different functions. Okay. Then the limit as I approach this value of one function plus another function, or one function minus the other function, either way, depending on what sign I want, is the same as me distributing the limit across each function. So if I take the limit as x goes to a of f of x, and I add that to the limit as x goes to a of g of x, or subtract them depending on which I'm using, it's the same. Okay, so that limit gets to distribute across to the functions, right? The limit as x goes to a of a constant times a function is the same thing as me being able to pull out that constant term and just finding the limit of my function. The limit as x goes to a of the product of two functions is the same as the product of two separate limits to that same value for my two functions. The limit as x goes to a of the ratio of two functions is the same as me taking the limit of one function over the limit to the same value of the other function. The only condition is that that denominator function can't be 0, right? We're still not allowed to have 0 on the bottom. Okay. If I am raising a function to a power and taking that function to a limit, well, that's really just kind of this number 3, but instead of f times g, it's f times f times f times f times f. So I get to kind of distribute this across, so I can just take the nth power of the limit of that function. I don't have to multiply my function times itself a whole bunch of times and then limit it. I can just take the limit of my function and raise that value. Remember, this is a number to the power of n. Okay. The limit of a constant as x goes to any value is just a constant, because a constant is always a number. So as you go from the left and the right, they're going to approach the same value, right? So the limit of a constant function is just that constant value. X is a continuous function. It's, kind of a polynomial. It's a first degree polynomial. So its limit is just a. I can always just plug in a to x and get out a. Okay. Same thing here. This is basically the limit of a power function. As we said before, it's a continuous function. So I can just evaluate it at a, because it's basically property 8 is basically property 7 mixed with property 3, or you can think about it as property 7 mixed with property 5, right? It's basically x times x times x times x. So that's really just a times a times a times, over and over again. Okay. So here n is a positive integer. Okay. Then we have the nth root. So it's the same thing again, because this is still a continuous function. So again, here has to be a positive integer as well, right? And we can extend this to the idea of a function. The nth root of a function as x goes to a is the same thing as the nth root of the limit of the function as x goes to a. Here again, n has to be a positive integer, right? So a lot of rules, but it's fine because you get used to them once you start to work with them. So what we're going to do is we're going to go over an example, and instead of just saying, oh, it's the continuous function, let me just plug this in, we're going to break down our function using these limit laws, right? The properties of limits, and we'll evaluate it using these properties of limits instead. So as an example, let's take 2x squared minus 3x plus 1. This is a polynomial. We know it's a polynomial. We know that it's continuous. I can just plug in 1 here. Okay, there's no problem with that. I'm not telling you to use this method we're going to go now over this method, but the method we're going to go over kind of lets you see why we can just plug something into a polynomial, right? That idea of continuity. So let's break this down according to the limit laws, right? So first and foremost, I know I can just plug in 1, and my limit will come out to 0. Okay, no problems there. Using the limit laws, we get the following, okay? This is an addition of functions. This is the first rule. This is one function plus another function plus another function. So I can break this down instead of taking the limit of one large function that's broken up as the addition of several functions, and I can separate that limit across the terms. Okay, so that's the first thing that we're going to do. Okay. Limit of 2x squared minus the limit as x goes to 1 of 3x plus the limit of 1. Right? So I can, instead of having it as one function, I can break it up into several functions. The other limit laws that I have is that a constant multiple of a function gets to pull out to the outside of a limit. That's limit law number 2, right? Constant times a function is a constant times the limit of the function. Okay, so this was me using the first rule. Here I'm using the second rule. This is 2 times x squared, so I can just pull out the 2 times the limit of x squared. I can pull out this 3. This is nothing times anything. We also have the property that the limit of a constant is just that constant value, right? That was number 6. The limit of a constant is always just that constant, okay? We also have that the limit of something squared is just that value squared, and the limit at x is just that value, okay? So we're really just showing you guys how this stuff works, okay? So here actually I decided to use this property, property 5, okay? That some function squared is the same as the limit of that function to the nth power, right? Some function to a power. So that's really just that an example of 8. Okay, so limit of x squared, I can say is the limit of x being squared. So I've broken everything down to the limit as x goes to 1 of x, right? Down to its most basic properties. So 2, 1 squared minus 3 times 1 plus 1, which is exactly the same thing we had here, which is going to be 0, right? Same thing. Remember, the limit of x is the limit of 1, which is the same thing here, which is just 1.